examples on relations. Okay, the first example. If R1 and R2 are relations in a set, if R1 and R2 are relations, let me write, just wait. R1 and R2 are relations in a set A, then R1 and intersection R2 is an equivalence relation. If R1 and R2 are, if R1 and R2 are equivalence relations, in a set A, then show that R1 intersection R2 is an equivalence relation. Right? So now we're going to prove this. Let R1 and R2 be equivalence relations in a set A. So that means R1 and R2 are reflexive. This means that R1 and R2 are reflexive. R1 and R2 are symmetric, and R1 and R2 are transitive. Right? This is what is meaning of it. Since R1 and R2 are reflexive, therefore, AA belongs to R1 and AA belongs to R2, or all A belonging to A, and which means that this AA belongs to their intersection for all A belonging to A, and which means that this R1 intersection R2 is reflexive. Right? This is our first point. Now we are going to prove that this is symmetric. Let AB belongs to R1 intersection R2. That means R1 intersection R2. That means this AB belongs to R1 and AB belongs to R2. But R1 and R2 are symmetric. And this gives us that BA belongs to R1 and BA belongs to R2. But A and B, that means BA belongs to R1 intersection R2. belongs to R1 intersection R2, right? A and B belonging to A are arbitrary. These are the arbitrary elements. Therefore, AB belongs to R1 intersection R2 implies BA belongs to R1 intersection R2 for all A and B belonging to A. And this gives us that R1 intersection R2 is symmetric. This is our second property, right? Then the third property, let AB and BC belongs to R1 intersection R2. That means AB and BC belongs to R1 and AB and BC belongs to R2. But R1 and R2 are transitive. And R1 and R2 are transitive. And this gives us that AC belongs to R1 and AC belongs to R2. That means AC belongs to R1 intersection R2. Now A, B, C belonging to A are arbitrary. Arbitrary. That means therefore AB, BC belonging to this R1 intersection R2 implies AC belongs to R1 intersection R2 for all A, B, C belonging to A implies that R1 intersection R2 is transitive. So thus 1, 2 and 3 imply that this R1 intersection R2 is an equivalence relation. In SIT. Now we are working to second example. He says this, let R be the relation. Let R be a relation on the set A of ordered pairs. Set A of ordered pairs, right? Of positive integers. Ordered pairs of positive integers. Positive integers. Integers defined by this xy is related to uv if and only if. It's we can write if and only if IFF, or we can write if and only if this xv equal to yu, right? This is what is here. This is for xv equal to yu. Then show that R is an equivalence relation. That R is an equivalence relation, right? Let clearly this, let xy, now we are going to prove this, solve this or prove this, let xy belongs to A, which is a set of ordered pairs, right? or x and y belonging to the ordered pairs of positive integers. Okay, so this is here. xy belongs to A. Now he says clearly xy belongs to A. We know that xy equal to yx because xy belongs to the set of positive integers, and the set of positive integers is commutative under multiplication. Is commutative under multiplication. And this gives us that xy equal to yxy. xy is related to xy. xy equal to yx, right? So it's related to this. And xy belonging to A are arbitrary. xy belonging to A is arbitrary. That means xy is related to xy for all xy belonging to A. And this means this R is reflexive. Second property, that it is commutative. Let xy and uv belongs to xy and uv. This is xy is related to uv. This is given to us, right? That means this means xy, xv, sorry, not y, xv equal to yu, right? Since x, y, vu or uv belongs to the set of positive integers, and the set of positive integers is commutative under multiplication. Therefore, we can therefore Vx equal to Uy, and that means we can write Uy equal to Vx, and this gives us that Uv equal to x. Uv is related to xy. Now xy and uv belonging to A are arbitrary, implies that are arbitrary. Therefore, xy related to uv implies uv related to xy for all xy and uv belonging to A. And this gives us that this relation is symmetric. This is our second point. Now we are going to prove the third point. Let xy and uv, let xy related to uv and uv related to rs, right? For xy, uv, rs belonging to A, right? Here the xy, uv belonging to this is for xy, uv belonging to A. right? So and this gives us that this xv equal to yu and us equal to vr. Since v is u and v are non-zero, therefore this gives us that x equal to y u by v and s equal to v by u r. Now consider xs. xs. Substituting x as y, v by u. Substituting s as v, x as u by v, and s as v by u r. So that means this xs equal to yr. And this gives us that xy is related to this, xy is related to rs, right? xy uv and rs belonging to a are arbitrary. xy uv and rs belonging to a are arbitrary. So this gives us that this is this. Therefore, xy related to uv and uv related to rs implies that xy related to rs for all xy, uv and rs belonging to a. Y, uv and rs belonging to a for all. This is a symbol for all. And this gives us this R is transitive. This is R3. So R is transitive, R is symmetric, and R is transitive, R is symmetric, and R is reflexive, implies that R is an equivalence relation. Right? So it is an equivalence relation. So R is an equivalence relation. Now we are coming to the another example, right? He says let X be the set consisting elements 1, 2, 9. And R1 be a relation on X. On X or in X given by that R1 consists the difference of xy, which is divisible by, means xy are the elements chosen from X such that the difference between them is divisible by 3. This is what you say, right? and R2 be a relation on X, right, given by this R2 is again chosen, the elements are chosen from X such that the elements XY are either from this 1, 4, 7 or XY are from this 2, 5, 8 or this XY are from this 3, 6, 9. Right? Then show that R1 equal to R2. Then show that R1 equal to R2. Let XY belongs to R1. That means X minus Y is divisible by 3. It means that X minus Y equal to 3k, where k is an element of, is an integer of Z basically. That means the X minus Y equal to 3k for k belonging to the set of integers, right? If k is 0, that means X minus Y is 0. And that means X can be 1, that means X equal to Y. Means it can be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 8, 8, 9, 9. Right? So that means X can be this chosen from this 1, 4, 7 or XY can be or XY can be the subset of this 2, 5, 8 or the XY can be the subset of this 3, 6, 9. Right? We make this 1. Okay. Now, if k equal to plus minus 1, right, then we can see that the 4 minus 1 is 3 and the 1 minus 4 is minus 3. Okay. 7 minus 4 is 3 and this 4 minus 7 is minus 3. We can see that this is this 1 minus 4, 7 minus 4, 4 minus 7. Similarly, we can see here this 2 minus 5 is 3, right? And this 5 minus 2 is minus 3. Then we see that 5 minus 8 is 3. And this 8 minus 5 is 5 minus 8 is minus 3, and 8 minus 5 is 3, right? Then we can see here that 6 minus 3 is 3, right? And 3 minus 6 is minus 3. Then we can see that this 9 minus 6 is 3, and the 6 minus 9 is minus 3. So it covers. It means that XY can be chosen from, can be 1, 4, 7. XY can be this 2, 5, 8. XY can be this 3, 6, 9. 3, 6, 9. 3, 6, 9. So if k is minus 2, plus minus 2, that means the XY, if k is plus minus 1 means, if k is 0, that means X minus Y is 0. If k is this, that means the X minus Y is plus minus 3. So these are the outcomes. So if k is plus minus 2, that means X minus Y is plus minus 6. Means this X minus Y is plus minus 6. So we can see here this 7 minus 1 is 6, and the 1 minus 6 is minus 6. And similarly, this 8 minus 2 is 6, and the 2 minus 8 is minus 6. And then we have this 9 minus 3 is 6, and the 3 minus 9 is minus 6. This is what we have. And this again, this xy are either chosen from this 147 or from this 258 or from this 369. So 1, 2 and 3 imply this xy belongs to R2, but xy belonging to R1 is arbitrary. That means the R1 is contained in R2, right? Now on the other hand, let xy belongs to R2. That means this xy are chosen from this 147 or this 258 or xy are chosen from this 369. So we can see that this y minus x or x minus y, we can see the difference between this x minus y. If it is chosen from this as either 0 or 3 or 6, right? Either they are chosen from this 147 or from 258 or from 369. That means the x minus y is divisible by, or the y minus x is divisible by 3, right? Let me see what is in the R1. It is x minus y or y minus x. So that means the x minus y is either the x minus y or the y minus x. What is written in the question? X minus y is divisible by 3. I have written x minus y. So let me, x minus y is divisible by 3. Right. So this gives us that x minus y is divisible by 3, and which means that x and y belongs to R1, but xy belonging to R2 is arbitrary, implies that R2 is containing R1. This implies that R2 is contained in R1, right? So A and B imply that R1 equal to R2. So A and B imply that A and B imply that R1 equal to R2. This is what is the proof. So I stop here. Okay, let's see. So I wind up here. Thank you. I hope you enjoy the class.